This is Professor Stephen Nesheva again, and I'm here to help you out with sample calculation number 2 of the decomposition of hydrogen peroxide lab. This is the thing we've asked you to do. If you've measured the change that in the pressure in the test tube of 0.01 atmosphere per second, then what's the reaction rate? And in order to do that, we have a couple of equations, 2 and 3, that will help you out on that. And those are in your lab handout. I'll come back to those in a minute. Let's bring up Excel first, though, and you'll see that I've added a few more items here. I've added a volume of the air, which obviously is the volume of the test tube. Take away however much aqueous solution is in there, so that's 30 mils. I also added a column for the degrees of the solution in Kelvin, because we'll be needing that, and then a few more columns here. That's the rate of the pressure increase. Don't worry about the Greek deltas. You can just put in D's for that if you like. So let's see. The first one, I just want to just check to see how you're doing on this. You want to do a calculation based on the degrees Celsius and do a fill down. Why don't you try that? Okay. Here we go. I'm going to say that's equal to the degrees in Celsius plus 273. And hit return. That looks pretty good. And now I'm going to go into the lower right, double click, and that gives me those temperatures. Okay, how about this? Well, this first number I'm going to put in is 0.01. That's what we have in the exercise as the rate of pressure increase. Of course, that's going to be something that you'll measure in the lab. For the second one, now let me go back to our the handout. This says, that's equation 3. It says if you know how fast the pressure is increasing, then multiply it by 2 times the ratio of volumes, RT, and that will give you how the concentration of hydrogen peroxide is changing. Okay, so let's do that. I'm going to, well, if you want, give it a shot, and we'll come back in a moment. Okay, so here's my try at this. I'm going to say is equal to minus 2 times, now what was upstairs? It was the volume of air. That was 30 mils. Now I'm going to divide by, and there's a few things in the denominator. First one was R. Now in this case I'm going to use, because the gas constant in liter atmosphere is 0.082. And times the temperature, well, and it has to be in Kelvin, so I'll click on that box. That's RT, and now the last thing, I need the volume of the solution itself, which, of course, we've decided is 5 mils. And that's that, and don't forget we want to multiply it by the rate of the pressure increase by itself. Okay, so there's that number. Now, as before, since I don't want these volumes to fill down, everywhere that I see one of these B guys, I'm going to change it to an absolute address. There we go. I think the rest of that looks pretty good. Okay, and then let's see what was. Oh, we're getting a negative number for the delta hydrogen peroxide. That's okay. That's fine. That's because the hydrogen peroxide is disappearing, so the concentration is going down. The rate, let's see, what did we see in our handout? The actual rate in this equation, equation 2, says take how fast the hydrogen peroxide is changing and multiply it by -0.5. So why don't you give that a shot? Okay, here's my attempt at it. It will be -1/2 times that rate right there, and return, and there we get our number. That's the rate in moles per liter per second of, that's the rate of the reaction.